All right, everyone, we're on to chapter 2, and in chapter 2, we get into a kind of a key part of geometry. We get into proofs, and that starts with inductive reasoning. So today we're going to describe patterns and use inductive reasoning. We're going to be able to draw the next figure in a sequence, and we're going to be able to predict the next number in a sequence and explain the pattern. So today is basically just looking for patterns. So a few definitions. A conjecture is an unproven statement that is based on observations. All right, so it kind of be like you are doing a study on something. It could be how people feel when something happens to them, like and you observe their behaviors. That will be one study. So conjecture is, again, what you're basing off of observations, what you're going to say is happening. So in order to be true, it must always be true. Okay, so for example, you can't say like eating McDonald's will make you gain weight, because there are some people out there who eat McDonald's and they don't gain weight. So in order to be something that is true, it has to always be true. So making that statement would be incorrect. Eating McDonald's can obviously cause or make you gain weight, but you can't say it's going to make you gain weight. It can definitely help in that, though. So that's just one example. Inductive reasoning is the process of finding a pattern for specific cases and then writing a conjecture for the general case. So we go back to that McDonald's case. So if you are a few of your friends have been eating McDonald's, and you notice that over a few months they've gained some weight. Based on seeing numerous friends eat McDonald's and gain weight, your conjecture would be, based on seeing my friends eat this, I am assuming that eating McDonald's will cause you to gain weight. A counterexample would be a specific case for which the conjecture is false. Okay, so using that same observation. So you're saying eating McDonald's will cause you to gain weight. A counterexample would be somebody who eats McDonald's all the time or has eaten McDonald's regularly and they do not gain weight. So that would be a counterexample showing that, wait, that's not true all the time, so don't say it's true for everything, for everyone. All right, so example 1, describe how to sketch the fourth figure in the pattern, then sketch the fourth figure. So you look at figure 1, figure 2, and figure 3. How would you describe what's happening? And we can keep it short and sweet. There's a few ways to say this, but I would basically just say adding 2 more boxes each time, or breaking into 2 more boxes each time. Adding a column of 2 blank boxes. So figure 4 would now have 8 of them. It'd be the same size. It would have 8 columns. So it'd be splitting into 8, like so. And just the bottom left corner is still the one that's colored in. So that'd be figure 4, based on the pattern. So we're saying that adding the 2 blank columns or 2 blank boxes to the right would look like this. All right, the checkpoint. Sketch the figure in the pattern below. What's the next figure going to be? So we have a square, and as you can see, we draw a circle inside the square that's not filled in. Then we draw a square that is filled in. Then we draw another circle inside that's not filled in. So the next one will be, so you have your square, then you have your circle. This drawing is not going to be good. Then you have your square, and you have your circle, and you're going to have another square then. Oh boy, this is not going to be pretty, but I'm going to make it work. So every corner of the squares are colored in, and the square on the inside is colored in, but all the parts of the circle are not. And that was a horrible drawing. Let me try that one more time. So square and a circle. Square, circle, square. This really ain't much better, but kind of can see. Okay, so basically you see that it's going to be one of these two. And let me erase this one that's smaller. I don't like that. So it's going to look about like that. So you put the same picture as here, but you draw a square in it. That's the pattern we're seeing. Example 2, describe the pattern and then write the next number. So what's happening when you go from -1 to -4? And then from -4 to -16 and -16 to -64. What's happening? It looks like each of these is going to be multiply by 4. Right, that's the pattern. -1 times 4 is -4. -4 times 4, so times 4 times 4 is -16. -16 times 4 is -64. And -64 times 4 is -256. Right, and then we have the checkpoint. Describe the pattern in the numbers 1, 2.5, 4, 5.5, and then write the next number in the pattern. So what is happening when you go from 1 to 2.5 to 4 to 5.5? And I'll tell you, usually you're adding, multiplying, dividing, or subtracting. That's what's usually happening. So in this case, it's plus 1.5 each time. So add 1.5 each time. That's the pattern. So what's the next number going to be? 5.5 plus 1.5 is 7. So the pattern is add 1.5 each time. The next number is 7 in that pattern. Okay, example 3 is kind of tricky. I don't mind the problem, it makes you think, but it can be a little tricky for you. So on the top, it says number of points. So we're just going to list 1 point, 2 points, 3 points, 4 points, 5 points. So like I'm thinking like points in geometry. So our picture of 1 point is going to look like this. How many points or how many dots do you connect if there's only 1 point? So the number of connections is how many you can connect. So for example, if you have a bunch of dots, how many connections can you make between those dots is what we're kind of looking for, right? So how many different connections are there? If there's only 1 dot, there are 0 connections because you can't connect that dot to another dot because there's not another dot there. But if we have 2 dots, 1, 2, how many connections can you make that are segments? Just 1. You can connect those 2 dots. Okay. And there's no other connections we can make. What if there are 3 dots? How many connections can we make? So there's 1, 2 connections with those, and then there's a third connection we can make. So each dot can go to all the other dots. So there are 3 connections. They form a triangle. Okay. What if there are 4 dots? 1, 2, 3, 4. We have to count how many connections there are. So I start in the top left. There's 1, 2, 3 connections to make. Then I go to the top right. There's 1, 2 more connections I can make that aren't already made. Okay, then we go to the bottom right. There's 1 more connection. So let's count how many there are total. There's the 4 on the outside and the 2 in the middle. So how many are there? There are 6 total. And the next one gets even trickier yet. What if there are 5 dots? 1, 2, 3, 4, 5 dots. Okay, so obviously we have 1, 2, 3, 4, 5 connections. And then that's on the outside. Now we have the ones that go through the middle. 6, 7, 8, 9, 10. So there are actually 10 connections when there are 5 dots. Okay? So if we're going to look for the pattern, we're going to look for the pattern of connections. So from here, it goes up 1. From here, it goes up 2. From here, it goes up 3. From here, it goes up 4. Okay? So what would the next one be? What happens if there were 6 of them? What would the next one be if there were 6 pairs? It would be up 5. Okay, so to make a conjecture, our conjecture is that it goes up by consecutive numbers. +1, +2, +3, +4, +5, and so on. So that's our conjecture. How many connections would be made if you were to connect different pairs of 6 collinear points? Well, that's what we found out right here. Whoops. I didn't want to do that. Undo. That's what we found out right here. So there would be, since it goes up by 1 more, there would be 10 plus 5 more. So there would be 15 connections. All right, in example 4, it says we're going to make and test a conjecture. So numbers such as 1, 3, and 5 are called consecutive odd numbers. So the odd numbers in order are 1, 3, 5, 7, 9, 11, 13, and so on. So we want to make and test a conjecture about the sum of any 3 consecutive odd numbers. So like, what if we took 1 plus 3 plus 5? What would we get? We would get 9. What if we took 3 plus 5 plus 7? Those are also consecutive odd integers. So 3 plus 5 plus 7 is 15. Okay. What happens if we took 5 plus 7 plus 9? We would get 21. And you can keep doing this and seeing what happens. We're just trying to form some idea of what's going on. Is there a conjecture we can make? So step 2 is make the conjecture about the pattern. So what do you notice about the numbers you get? What do you notice about 9, 15, and 21? What is true for all of them? Well, all are odd. Okay. What else do we notice? All are divisible by 3. So all are odd and all are divisible by 3. So now if we test our conjecture, let's try to pick some other odd numbers that are consecutive. So what about like 11 plus 13 plus 15? Those are all odd. 11 plus 13 plus 15 is 39. So 39 does work out because 39 is odd and 39 is divisible by 3. Let's try other random ones. Let's do 15 plus 17 plus 19. What is 15 plus 17 plus 19? 51. So 51, if you divide it by 3, it works out, and 51 is odd. So it does work out for the 2 tests we did, right? So now, we obviously don't know if, we can't test every single possible group of odd numbers, but it's working out so far. So checkpoint 4 says, make and test a conjecture about the sign of the product of any 4 negative numbers. So step 1. Step 1 is to find pattern using groups of small numbers. So what happens if we took 4 negative numbers?